Okay. Well, hello everybody. Welcome. Hope you had a nice weekend. So, if you remember on Friday, we mostly did a whole bunch of example of Gauss's law in different geometries and different situation. And as said, we had still one last geometry that was interesting to do. It was basically a sphere, a homogeneous sphere, which is another common example. So I think we're not gonna go in details about that because you will do that. This will be part of next on the discussion next week. You'll have an example that will use an insulating sphere, so you can just you'll be able to do it then. And we did a lot of examples of this Gauss's law application like last Friday, so no need to do it twice on that geometry. Still, I mean, if still interesting, I'm gonna give the final results, so then we can kind of use that in other situation. But so if you remember, I mean, as every time we use Gauss's law, we just relate the electric flux across a closed surface to the charge enclosed to this surface, and assuming some kind of symmetry and using a Gaussian surface that's has a matching symmetry, we can retrieve the electric field. And for doing the calculation at Escape, you're going to be doing them on Wednesday, so don't worry. And then you obtain a result that's similar to what we got with the cylinder. I don't know if you remember, like last Friday, we did uh, the cylinder that had a volumetric distribution of charge, and we saw that when we are inside the cylinder, we would have a linear increasing electric field when we get until we get to the surface of the insulator, and then outside of the charge object, the electric field would just decrease. And we obtain a similar trend with the sphere, but a difference here is that now the electric field is dropping as R squared, while it was dropping as just 1 over R for the cylinder. So that's a one difference between the two. And if you apply this, I mean, the method we've used, and uh, you you'll have to differentiate if you're inside or outside of the sphere, just because when you're inside, the actual enclosed charge depends on the radius, and when you're outside, it's just the total charge of the sphere. So that's why you have to differentiate, and if you do that, you'll end up with that result. So I'll still leave it on the slide if you wanna, practice, do it before Wednesday, or use that as an example and may see it in details. But yeah, since you're gonna be doing it as an exercise, we can move on. So applying this result, from the sphere, let's look at this example. And now we have a slightly more complicated situation because we have an insulated sphere that is charged with a charge plus Q at the center, but then we have a surrounding thin shell that has a charge minus Q divided by 2. And so we see that it adds some complexity to the overall configuration. It still has a spherical symmetry. So which one of these following plots best represent the electric field as a function of the radius? I give you 10 more seconds to think about it, give your answer, and then we go over the actual answer. Okay. So majority of you guys, next one change. Majority of you guys answered the choice number 3. So let's have a look, more detailed look. So we have a spherical ball here, it's charged, and then we have another charge that is distributed around it. So first let's look at the first part between 0 and R0. So we've just seen if we apply Gauss's law to the sphere, and inside the sphere we have a linear evolution. So this is correct. It's the same for all of them anyway. And then if we take a Gaussian surface around, like between the two radius, imagine this is a spherical Gaussian surface, then we just have the similar situation as we had in the case of the lone sphere. We just are getting away radius that increases away from this center, and the enclosed charge remain constant, just the charge of this. But then when we get outside of the radius here, now we see that we have a change, because now the enclosed charge is not plus q, but plus half q. And so everything will still behave as like the overall charge is just a point charge at the center, and we're getting away from it, and with a distribution in square. But now it looks like the charge at the overall charge is not plus q but half q, and so we have a drop there's a drop in the electric charge in the electric field here that corresponds to this enclosed charge, because here we have an enclosed charge of q, here we have an enclosed charge of q divided by 2, and so the right answer is the answer number 4, because this accounts for this drop in electric field in enclosed charge. And it might seem weird to you that we have this discontinuous jump in electric field, and I mean, as you know, usually discontinuity don't really exist in nature, but actually we assumed a very infinitely thin shell of for this, but it would still have some thickness, and therefore it would just be a drop, a very abrupt drop between those two. So if you look from far away, just get this evolution with a drop between, I mean, just at the position of the shell. Okay, yeah, we have a questions. Why does the electric field increases as you get further away from the center? And so if you remember, we have Gauss's law that tells us that the flux E dA over a closed surface is equal to the enclosed charge divided by epsilon 0. So this is the enclosed charge. And so as we get further away from the center, when we get our Gaussian surface to obtain this electric field, we see that we enclose more and more charge from the sphere, because here we have a small portion of the total charge from the sphere. But if we use a larger Gaussian surface here, we see that we enclose more charge, and so we increase this electric field because we have more flux. And when we get to the edge, and then when we get away from the when we have a when we're between the shell and the sphere, then when we increase the radius, we just keep this same charge constant. The enclosed charge remains the same, but now the area of the Gaussian surface is larger. And so we just we have a decreasing electric field because we keep the same flux and we increase the area. So we decrease the electric field. And yeah, an additional thing to understand why, just an easy way, it's linear, it's a linear increase. And because there's competition when you increase the radius of your Gaussian surface, when you're inside the sphere, there's a competition because you increase the charge you enclose, but you also increase your area. And so you reduce so if you increase your area, that means that decreases your electric field to keep the same flux. But what's happening is that since it's a sphere, it's a volume, when you increase the radius, you increase the charge enclosed. The charge enclosed evolve with R cube, while the area evolve with R square. And so that leaves you with still a gain of electric fields. The ratio you still have to have E that increase as a factor of R to match with the increase of enclosed charge. So that's an interesting thing to understand, is that this increase of understand the competition of the enclosed charge and the increased volume that leads up to the that matches with the electric field. And since it's volumetric for the charge, it's R cube, and it's an area for the flux, so it's R square, so it leaves us with an R remain. Okay, let's no, not now that we clarified a few things on that, let's see another kind of more complex situation. So now we have a charge Q that is spread inside this sphere here, and then we have a thick shell of radius R2 here. So here, the charge minus Q is uniformly reparted in the, uniformly distributed in this thick shell here. So how does the electric field evolves when we're increasing the radius? Okay. Okay. This time seems like you mostly got it. You answered the choice number 3, which is the correct one. Let's again go step by step. So if we're increasing the radius to get to R1, then see, it's the same situation with as the sphere. We're inside, we're increasing the radius, so increasing the enclosed charge, so we're increasing the electric field. And once we get to the shell, the thick shell, when we increase the radius, now, let's take intermediate Gaussian surface. Now the enclosed charge is Q minus a fraction of the outer shell charge, which is minus Q. So it will be smaller than Q, but higher than 0. And so we see that as we increase the radius, the charges decrease up to the point where we get at the exact area outer shell of this charge. And then if we get the enclosed charge in our Gaussian surface that's larger than this R2, we see that the enclosed charge is 0, and therefore the electric field is 0 too. So, or more precisely, in that case, the electric flux is 0, and since the symmetry and everything is symmetric, the symmetry is spherical, and we can extract the electric field because of this symmetry. We can deduce that the electric field is 0, but be mindful that 0 electric flux doesn't necessarily equate to a 0 electric field, because, for instance, we've seen that for the dipole, it still has an electric field at any radius that equals r divided by 3, r to the power 3. But the net charge is 0. But in that case, it's because it has symmetry, and so we can still extract the electric field because of the cylindrical spherical symmetry. The electric field is constant at the radius, and so we can get it out of the integral, and therefore we see that in that situation it leads to the electric field being 0. Okay, and let's add another layer of complexity. And now we have a charge plus 2q that is distributed in the core of a cylinder of radius r1. And then we have a thin sheet of charge minus q, and then a thin sheet of charge plus q. So how does it evolve with the radius? All right. You're correct. It's the situation number 2. And I mean, up to the first shell is the typical case we've seen with a small increase, and then it's now a decrease, but it's a slower decrease than in the spherical case. If you remember when we did the calculation for cylinder, this decrease as 1 over r, not 1 over r square. These just come from, again, dimensions of the thing of the system. But then if we're between the two shells, now if we take a Gaussian surface between the two shells, the enclosed surface decreases from 2 q's to just 1 q. And so we have this drop here that corresponds to this drop in charge, and because the flux depends on the enclosed charge. And then when we pass through the other shell here, now after the other shell, the enclosed charge is back again to being 2q, because we have 2q minus q plus q, which ended up being 2q. And so we have the same enclosed charge as before. And so it just takes, it increases the electric field here and evolves in the same way as it was doing before when the enclosed charge was 2q at the beginning. So yeah, you see there can be a lot of different, complexity, different cases that you can create using this case. And basically, the two main questions you have to uh, ask yourself is, what is the symmetry of my system when you want to apply Gauss law? And what is the enclosed charge in my system? And using those two informations, you should be able to retrieve the electric field when it's possible, and at least know and intuit the evolution of the electric field. Okay. And I think it's yeah. Yeah, I might have spoiled. We'll see. But I know a lot of polls right now, but it's just to confront you to different cases that can arise. So this one is a bit special because we have a charge Q that is present on a thin spherical shell of radius r. And so which of these electric fields would best correspond? Okay. And so we mostly answered this case, and yeah, that's correct. And because we have a spherical symmetry, and so if we take Gaussian surface inside here, we know that the electric field depends only on the radius because we have spherical symmetry. And so yeah, and we see that the enclosed charge the enclosed charge in our Gaussian surface is just 0. And so we have E ds equals 0. And actually here, because E is constant over the radius, because that's a point of symmetry, we have E ds integral of ds is 0. And this is just the surface of our sphere. So this is obviously non-zero. And so that means that the electric field has to be 0 for this to be 0. So yeah, that's because there's no enclosed charge here, no electric field because of the symmetry. Okay, so if you remember on Friday, I specified, I made the point of specifying that we were doing those calculations, and especially in the volumetric cases, that where for instance, the cylinder was an insulator. And some of you had some question about that and why it was important. And my answer was that because the charges in conductors, the electron can freely move, uh, this creates different conditions. And mainly is that in a conductor, because the charge can freely move, the electron can freely move, a net charge on a conductor or in a conductor, depending, it can only exist at the surface. And that's because if you have a specific, let's say, negative charge here, they're gonna repel each other, and so they want to get as far away as possible, and they can freely move. And so the way for them to get this repelling force the minimum as possible is to just go all the way to the surface and end up being there. And then once they're at the surface, they cannot get out of the conductor because the conductor charge are still attached to the material. They can freely move inside the material, but they cannot get ejected from the material. And so you end up with if this is a cross section, you just get the charge that ends up being repelled on the edge, and inside there is no net charge. There's still, I mean, of course, it's atoms, so there's still protons and electrons and that exist, but they exist in a way that they have net charge of 0, meaning that as much positive charge as negative charge. So overall, the center or the inside of the conductor is not charged, and if there's any charge on the conductor, it's on the surface. And we see that it will obviously change the situation, because now if we have this ball sphere of conductor that has some charge, the charge is located at the edge. And so let's consider our spherical, we are still in a spherical geometry. So let's consider Gaussian surfaces that are a sphere around or a circle around our sphere. And I mean, they continue here in the drawing. It's just part of them, but I mean, they continue and they are enclosing this sphere. And so if we do that outside of our conductor, then the situation ends up being the same. We have spherical symmetry, so we can, the electric field will depend only on the radius, and we end up obtaining that the electric flux is just the electric field at a specific location, at a specific radius, multiplied by the radius, the area of the Gaussian surface. And by using Gauss's law, we have that this is equal to the enclosed charge divided by epsilon 0. And this is the same as the point charge. This is the same as the spherical insulator. And so this is outside of the sphere, but now let's think at what's happening if we are inside the metal. Then, if the radius of our Gaussian surface is smaller than the radius of our sphere, of our conductor sphere, then the enclosed charge is exactly 0, because we just said that all charge in a conductor must be at the surface here. And so if we have an enclosed charge of 0, it means that we'll have the electric field that will be 0. And therefore, there is no electric field in the conducting sphere. And if we just have a radius, if we're outside of the sphere, we have the enclosed charge that is Q. And so we are just in the same case than for the point charge or the spherical insulator that has a uniform charge. So we see that difference is really inside, and basically this comes back to this. There is no electric field inside, and you can even remove sphere. There is no electric field inside conductors. And so if you look at your spherical case, a spherical conductor case, then outside you have the usual decreasing electric fields that evolves at the 1/r square, and inside we have just 0, and there is no electric field inside the sphere. And this can be generalized to any geometry of conductors. There is no electric field, no charge inside a conductor when it's at the equilibrium. And we are doing electrostatics, so we are considering only equilibrium situations. So yeah, John, basically it behaves exactly like uh, the hollow shell case for in that situation. Just basically just as a if you're considering just enclosed charge, here it's just 0 inside that sphere. So yeah, in here, if we're considering and here we see another interesting thing that can arise when you're considering conductors in the context of Gauss's law. So here we have a conductor, and usually it has just a random geometry, and because it's a conductor, because it is a conductor, then the electric field is 0. Another way to understand why the electric field in a conductor is 0 is that if you had a non-zero electric field inside the conductor, then because it's a conductor, the charges can freely move, and therefore they will be accelerated by this electric field in a way that they will be moved and will negate, will come and oppose this electric field, and then you end up with the case where the only case where you will have equilibrium is when you don't have any electric field, because otherwise the charges will be moving and accelerated by the electric field. But then when they get on the outer shell, then it's not like they can go further away, and so that's they end up being stuck on the outer shell. That's why here you can only have charge on the outer shell of the conductor. Okay, so now let's imagine that in our volume of conductor here, we have a cavity inside here. So here we have cavity, it's vacuum, or it's it's just not any material here, and we have this situation. So since here something I didn't mention, but we're considering the case where we have a conductor, and this conductor has a charge QC. And so here we imagine this conductor has a cavity, still has a charge QC. Okay. Then if we take the Gaussian surface inside the conductor, here we see that we have no enclosed charge, and therefore having a cavity here doesn't change the fact that we still have electric field equal 0 here. But now let's imagine that in that cavity here we place just one single positive point charge here. So here we have a single positive point charge. So if we take, we have a positive point charge. We take a Gaussian surface in the vacuum around the point charge, and then we obtain the usual expression for the electric field that depends, that decreases R square. But then when we take a Gaussian surface inside the conductors, we have that the flux across this Gaussian surface is equal to the enclosed charge divided by epsilon 0. And we've seen, that's one of the properties of the conductor is that the electric field inside the conductor has to be 0. So this is 0. And so obviously this has to be 0. And so it means that the total enclosed charge has to be 0 too. And so what's happening if you put a positive charge inside is that you're going to charge the inside, the inside edge of your conductor with negative charges here. So that when you take any Gaussian surface inside your metal, you have a net charge. This negative charge is going to be created so that it's exactly equal to the positive charge inside in amplitude. And so when you take a Gaussian surface inside the metal, you have a 0 enclosed charge and therefore a 0 electric field. But now, the metal had initially a charge, a positive charge, Q conductor here. And one of the property we saw in electric charge is that the charge has to be conserved. And now we have some negative charge that have been, have moved around here. And so to conserve the total charge now on the outer edge of the electric. So the question is, where do the negative charge comes from? So, basically in the conductors, positive charge will be, so in the conductors, we've seen it's a mesh, a fixed mesh of positive charge, which are the ions, the nucleus, the charged nucleus of the atom, nuclei of the atoms. And then we have the free electrons that can move, and the electrons are negatively charged, and that can freely move in the metal. And so in that case, usually only the electron can move. And so when you have a negative charge, basically means that some electrons from here moved to that position. So here you have an excess of electrons, and here you lost some electrons here because they moved here. And so you gain, the amount of electrons that you have in excess here, they had to be taken from somewhere. And so here you find that the now positive charge on the outer shell is QC, the initial positive charge, plus the equivalent charge that has been placed around the cavity. And so overall, your conductor still has, if you just sum the total charge of your conductor, is still QC, because it's QC plus Q minus Q. So yeah, the charge in your conductor hasn't changed, and that's because the charge has to be conserved. But the charge distribution in your conductor has organized so that the electric field inside of the conductor is 0, because it has to be. Does that make sense? It's I understand that there's a little bit more of conceptual complexity, because now it's a more dynamic case where the charge can evolve, the location of charge can evolve depending on the situation to just remain at equilibrium. So kind of. So yeah, I guess it's doesn't really, it's not extra clear. So What's what's not clear? I guess because if it's kind of clear, it's not clear. Okay. Let's see. So we have our metal here, and we have the cavity, and we put a positive charge inside the cavity. And let's imagine the case where the metal has no initial, it's just neutral. Yeah, the electrons, I mean, as you know, matter, I mean, there's always electrons. And in one of the first slides of the chapter on electric charge, we've seen that model to describe, a metal would be, a mesh of positive charge, which are the nucleus from the atom. It's taking a long time to draw, but a mesh of fixed positive charge, and then you have electrons that are kind of almost like a fluid of electrons that can move freely in that mesh of charge, and basically they want to keep neutrality, but they still can move. And then if you put, let's say, a positive charge, something that is positively charged here, then electrons are going to be drawn toward this positive charge because it's attracting them. And so you end up creating a residual negative charge on this side, on this side of your conductor, because they are attracted to the positive charge. But in your conductor, you only have a fixed amount of electrons, and basically you have enough electrons. If it's neutral at the beginning, you have as many electrons as you have positive charge that are given by the number of atoms and protons in your solid. So you have a fixed amount of electrons, and so if you lose and if you concentrate electron at some point, then on the other side you'll have less electrons, and so it will be positively charged because there's less electrons to compensate for the positive charges. And so by moving around your electron, depending on the other charge that are outside of your metal, because here, for instance, we put the positive charge here, and so electrons from the metal are attracted to this positive charge and gather up around the edge of the cavity. And therefore, these electrons, they have to come from somewhere, and they come from the metal, the rest of the conductor. And since charge can only exist at the edge, they must come from the outer edge of the material, and therefore the outer edge has lost electrons, and so it has even more leftover positive charge now because it lost some electrons, and so it ends up being even more charged than it was at the beginning. So let's look at an example to try and clarify this concept. So we have a conductor of an arbitrary shape, and it has a cavity inside, just like we just saw. And this conductor here has a net charge of 10 microcoulomb. So this means that, for some reason, this conductor has more positive charge than negative charge. So it has more proton than electrons inside of it. And inside the cavity, we put a charge that has Q plus 3 microcoulomb. So let's see what is going to be the charge on the inside surface of the cavity. So I guess on this surface, and what's going to be the charge on the outside surface. And one thing that we're clear about is that the charge in the conductor has to be, in that case, I mean, in any case, the charge inside, the material of the conductor has to be conserved. And so if it has 10 microcoulomb, with or without this, additional point charge that is in the cavity, the sum of the charges that are, Q out plus Q in has to be equal to Q, which is equal to 10 microcoulomb. This is because charge has to be conserved. You cannot lose charge in your whole system. Yeah. Okay, that's the first thing. And then since we've placed a positive charge inside the conductor here, this positive charge is going to attract negative charge here around the surface. And the resulting thing is, if we take a Gaussian surface in the metal around that, the enclosed charge from this and the negative charge that are gathered around the inner shell has to be zero, because the electric field inside the metal has to be zero. That's one of that's a governing law of the metal, is that the electrostatic field inside the electrostatic field has to be zero inside the metal. And so let's have a look at it. Let's first look at what's the charge on the inside of the cavity. So by Gauss's law, and that's what I was saying, the electric field has to be zero inside the conductor. And so the enclosed charge is zero. And so the charge in the cavity, which is 3 microcoulomb, plus the charge at the inner surface has to be zero. And therefore, the charge at the inner surface has to be minus Q inside the cavity, and so minus 3 microcoulomb. Okay. Yes, and then there's the second question about what's the charge outside of the metal on the outer shell. And we've seen that the metal or the conductor had an initial charge with or without the this center point charge here, that is 10 microcoulomb. And so this has to be conserved. And so if on the inside surface we have a charge of -3 that gathered, then on the outer shell here we have to have 13 microcoulomb, so that those 13 plus 13 microcoulomb minus those 3 microcoulomb on the inner shell ends up being the total charge 10 microcoulomb. Okay, is that clear? one second, sorry about that. Okay. Let's have a look at another example. So now we have a neutral spherical conductor of radius R2 that has a charge of 3Q inside a cavity here. So we have this conductor, it's neutral, so no overall charge, and we place a point charge at the center of the sphere. So let's now look at the electric field at 3 different positions. So first inside the cavity, and then inside the conductor, and then outside the conductor. So first, let's look at inside the cavity. In that case, it's that's what we've seen before using the typical case of Gauss's law. We have just the electric flux in a Gaussian surface that depends only on the enclosed charge. And then if we take a spherical area, then we obtain that we have basically the electric field that varies as in the same way as a point charge that would have a charge of 3Q. This is for inside, and that's basically the typical case of a point charge at the center of, at a specific location, and we're looking around this location. Then we switch to inside the conductor. And this is just basic properties of conductors that's inherent to their behavior and free electrons, that the electric field inside the conductor has to be 0. And to make that true, to make that possible while being compatible with Gauss's law, this means that there must be a charge of minus 3Q that is induced on the inside surface of the conductor. And this is so that the enclosed charge inside the metal is 0 because there's the plus 3 charge from the point charge center, and then the minus 3 Q that is located at the in the inside surface of the conductor to compensate for this and keep the electric field being 0. And now let's look at what's happening outside the conductor. Yeah. So since the conductor was initially neutral, the outside of the conductor will have a charge of plus 3Q to account for the minus 3Q. Minus 3Q that is on the cavity. That has been located on the inside of the cavity. And so we have plus 3Q, minus 3Q. And so we have an overall charge of 0, and that's because it was initially neutral. And so that gives, if we're outside of the conductor and we take the enclosed charge, then we have the charge that is inside the cavity, and then the charge that's at the surface inside, the charge that is at the surface outside. And I mean, this has to be, this is 0 because of, the initial neutrality of the point. And then it just ends up being the center charge. And so if we apply Gauss's law, we just end up having this situation where we take the flux of electric field around our Gaussian surface, and it's equal to the enclosed charge. And we end up with the similar situation as we are with a point charge, where we have this evolution of 1 over 4 pi epsilon 0, 3q divided by r squared. And so this is just the evolution of the electric field with the point charge at the center, and the point charge has a 3q charge value. So to summarize, inside the cavity, just behaves as if, it behaves with the same behavior as a point charge at the center. Then inside the conductor, the electric field is 0 because of the charge distribution that has evolved to negate this charge, enclosed charge, when you take a Gaussian surface. And then by neutrality of the conductor, you have the opposite charge. So minus 3q on the inside, plus 3q on the outside. And so overall, when you are outside of the conductor, it just looks like you have an enclosed charge of plus 3q. And so you just obtain the same behavior outside of the conductor than inside of the conductor. And you just have a drop of the electric field while in the conductor. Okay. So now let's look at the situation where we place a conductor in an electric field, but in what we could call an outside electric field. So now there's a distribution of charge plus and minus, positive line, negative line that creates a linear, field lines that are going from minus from plus charge to minus charge. And now let's place a conductor inside this electric field. So let's see what's happening. And so what's happening is, because of the electric field here, the plus charges here are attracting electrons from the conductors to this edge of the conductor. So here we have a negative charge that come to the edge, and here we have positive charge that are attracted by the negative charge here, or by, let's say, by the electric field. And so we create this situation where the field lines now end, the field lines have to start from positive charge and end on negative charge. So now field lines end here on this negative charge, and then there's no field lines inside because there's no electric field inside the conductor. And then field lines start from this positive charge here and continue outside and end up on those negative charge here. All right. And this situation works if your conductor is hollow inside. It doesn't need to be completely full, but if it's hollow inside but still completely enclosed by the conductor, if you just have let's say a box with a conductor all around, inside you have vacuum, then you'll still have negative charge that ends up being on one side, and that will be the termination of the field lines, and then you have positive charges here that will be being the beginning of new charges of the new field lines, and end up here. And inside, since the field lines are completely blocked and end up at the surface of the conductor, then you have a 0 electric field, even though you're not inside the metal, but just the field lines are blocked by the conductor. And And this is the principle of the Faraday cage, where you have basically an insulate a conductor box that prevents electromagnetic fields from getting inside the box, and that protect the inside of the conductor box from the outside electric field. But you see that it's not, I mean, it doesn't work. We've seen that it wasn't, it's a really different situation than when you have a charge on the inside here. Because when you have a charge on the inside, we just we just looked at the situation before, and the field lines, they just continue outside, because when you do your when you do Gauss's law, you take a surface like that, and you still have a net enclosed charge inside, so you still obtain an electric field that goes outside. So a Faraday cage does not shield electric field produced from a charge within. It shields from electric field from charges that are outside of the Faraday cage. And for instance, you might have heard that, when there's a thunderstorm, your car is a safe place to be in because it's a Faraday cage. And indeed, your car is a metallic box that is connected to the ground. And so if thunder, or if a thunderstorm were to hit if lightning were to hit your car, then it would just, the field lines from the electric field from the lightning would not be able to penetrate inside the car. It would just, just create some, put charges at the edge and charges at the other edge, and let electricity flow through it, but not inside of it. And that's why a car is a safe place during a lightning storm. It's because of the Faraday effect, Faraday cage effect from this conductor box. That's the same situation you can find with planes. And I mean, planes can usually be hit by lightning, and people inside will be more or less safe, because the electric field from the lightning cannot penetrate inside the shell of the plane, because it's metallic, and therefore it's shielded. I mean, it probably can be still dangerous for the overall plane and the electronics from it. So it's not like it's completely immune to lightning, but at least you're not at risk to get shocked by lightning when you're inside the plane. Okay, and since we're talking about lightning, I mean, this is kind of off topic, or at least really just a side note I want to make in the case of chargers, and since we're talking about lightning, because we see, I mean, air is usually a pretty good insulator. And so how comes that lightning can propagate, and can we have electric field that comes from the sky and reaches the ground during light storms? And that's because even though air is an insulator, if you apply a strong enough electric field on air, then you can basically rip off electrons from the atoms. Basically, you give enough energy to the electrons so they can just freely be ejected from the atoms, and you ionize your atoms, and you end up creating what's known as a plasma. And therefore, your matter is just gonna a gas of charged particle of charged electrons and charged ions that becomes extremely conductors. And so when that is happening, then your charges, flow in the electric field that, and now they can freely flow because it's conductor. And what they're gonna do is, because they flow fast enough, they're gonna ionize other atoms and therefore create a chain reaction that sometimes is called avalanche reaction, and create a line of ionizations that propagates the electric field, which is lightning. And this propagates up until the lightning is connected to the ground, and the charge can flow into the ground and neutralize the lightning. Same thing can happen when you get this small shock when you touch a doorknob or something that has been a bit charged. It's a similar thing that can happen, but on a much smaller and benign situation. And typically, the threshold field for this kind of ionization is on the order of 30 kilovolt per centimeter, so very high electric field. And if you have an electric field that exceeds this threshold, then you can have a breakdown. So just a quick summary on how to get electric field, how to calculate electric field depending on situations and the charge distributions. So basically a summary of the past week. So the first thing we did, that's probably the most basic and fundamental case is just adding multiple point charge. So if you have a distribution of electric charges up to a few electric charges, to get the total electric field, you just sum the contribution of each individual and each single particle charge you have. They each contribute to the electric field, and you sum everything, and you obtain the total electric field. So this was the first case, and I think that's what you did today during the. No, that's what you did Wednesday, I think. Yeah, that was what you did Wednesday during the discussion, and you see that if you pass like 3 or 4 or 5 charges, gonna become very tedious to do, right? It's just be doing a large sums with vectors, and it's becoming kind of tedious to do. When you get to more complex and charge distributions, it becomes necessary to integrate, especially when you have something where you have a distribution of charge that ends up being continuous. So you have charge along a line, as we've seen during the lectures, or in a disk or in a volume. Then you can integrate over a small element of charge dq that creates a small electric field dE at a specific location. And then you can integrate over all this small dE to obtain the total electric field E. And we've seen that this can lead to pretty complex integral calculations where you have to do some substitutions, and it can be complicated, but that's basically probably the most, you're going to the root of what creating the electric field, and you're summing all the contributions. So this will always work no matter the charge distribution, and then it just become a math problem and whether you're able or not to solve your integral. But this is a situation that, I mean, a case that will work with any charge distribution. And then in the past few days, we've applied Gauss's law, and this allowed us to get electric field of some charges distribution, and it was pretty easy and straightforward. Basically, all the integral calculation just came back to just getting the area of a specific Gaussian surface that we were considering. But applying Gauss's law to obtain the electric field is possible only when you have specific symmetries in your charge distribution that enable you to make assumption on the electric field. For instance, if you have a spherical charge distribution, you know that your electric field will depend only on the radial position and will be along the radial coordinate. And so, you know, if you take the right spherical Gaussian surface, then you know that it's constant along the whole surface, and it's always perpendicular to the surface. And so you can get the electric field outside and therefore obtain the electric field using Gauss's law. But if you have a random charge distribution with a weird shape that has no symmetry, you're not going to be able to use Gauss's law to obtain the electric field at any position using Gauss's law, because you need symmetries to get the electric field outside of the integral to be able to retrieve it from the enclosed charge. Okay, I guess we can stop here for today. So yeah, you might have seen I did upload new slides that was maybe planning on using for today, but it looks like it took the whole lecture to do this these cases of Gauss's law in conductors. And it's good because it's a more tricky point, so it's good that we took some time to understand what's happening. And starting tomorrow, I guess, yeah, tomorrow there's the quiz. So we'll briefly get started after the quiz on electric potential. And that's basically going to occupy us for probably the rest of the week, or at least until Thursday. So yeah. And I'll be keeping this Zoom on for office hours. So yeah, if you have any questions, you can stay there and ask me your questions. And otherwise, have a nice rest of your day.